We will be discussing the virulence and infectivity of COVID-19 through biological and mathematical means, exploring how the virus is spread, looking at a few mathematical models, and discussing potential treatment options. What is COVID-19? It is a newly discovered infectious disease which causes mild to severe respiratory illness. And the virus that causes COVID-19 is mainly transmitted through droplets generated when an infected person coughs, sneezes, or exhales. It is also known as the reason why you have been stuck at home for the past month. On the right, you can see the value of R0 for COVID-19 is about 2.8, which means an infected person on average infects 2.8 other people in a population where everyone is susceptible.
To cover the biology aspect of the spread of COVID-19, we can demonstrate biologically how infectivity occurs. So, in general, a virus particle will attach to a host cell and release its genetic information inside. This material uses the host cell's enzyme to replicate its parts. Once these particles have been fully replicated and assembled, these virus particles break out of the host cell towards others to increase their numbers. In the specific case of COVID-19 and SARS, these viruses interact with the renin-angiotensin-aldosterone system, or RAS, through an angiotensin-converting enzyme 2, or ACE2. This, according to the New England Journal of Medicine, is a potential factor in their infectivity. As shown in the image above to the right, ACE2 acts as a receptor for the SARS-CoV-19 virus. However, it inhibits RAS activation, and recent study of RAS inhibitors like ACE inhibitors and angiotensin receptor blockers are in recent debate in whether or not they should be used as treatment options for patients.
So we want a way to model the infectivity of a disease like the coronavirus. One main factor we use in these models is social interaction. This involves counting the number of people that you come into contact with on a daily basis and then using these interactions to predict the number of new cases per day. The graph on the right is from March 2020, and it shows some predictions for the new cases of coronavirus, depending on the amount of social interaction which occurs on a daily basis. We see that more interactions lead to a larger spike in new cases per day, whereas the decreased social interaction leads to a much flatter curve, which is the blue one on the right. To create models such as the social interaction model discussed on the previous slide, we need some concrete data. We can define the reproduction number or the contagiousness number of COVID-19 using the basic reproduction number R0. This number signifies the average number of people that an infected person can infect. A value of R0 greater than 1 means that one infected person causes more than one person to become infected. Until this reproduction number decreases, we will see a quick spread of the disease amongst people. The diagram on the right shows how infectious COVID-19 is compared to some of the other major diseases throughout history. The main factors used in mathematical modeling of viruses such as COVID-19 include the basic reproduction value, methods of transfer, and asymptomatic spread. When creating models, we must factor in the R0 value that was discussed in the previous slide. So accounting for the methods of transfer of a disease is very important as well. For example, if we realize that the coronavirus can be spread through surfaces, then it is likely that more people would contract the disease. Additionally, the asymptomatic spread of the coronavirus makes it extremely dangerous. This occurs when people who don't feel sick are actually carrying the disease, and then they can spread it to other people. So models must take into account the number of people who are self-isolating, as well as the number of possible asymptomatic cases. We'll look at some of these models in depth.
Now we'll talk about a well-known model used to predict infectious disease spreads. This is called the SIR model. In any given time, the SIR model partitions our population of interest into 3 different parts. The first part is the susceptibles. These are people who can get infected but are not infected at a given moment. When the pandemic starts, this would be everyone. Next, we have the infectives. These are the people that are infected at a given moment in time. We can see that the variable of beta shows the transition between susceptibles to infection. In other words, beta kind of tells you how quickly the spread is going. Next, we have the recovered. These are the people that have been infected but also recovered or deceased. As you can see, gamma is the variable we use to show the transition between infectious to recovered. And then finally, we have another variable with a dotted line for xi. This is to show the transition between getting infected, recovering, and then getting the virus again. This is only for infections that can happen multiple times. For example, for COVID-19, we are starting to see cases where some people get infected more than once. So we might need to think about this third variable, psi, if this is the case.
So this is a system of differential equations, which is the basic SIR model, and which we now explain. The top equation models the change in susceptible individuals over time. It says that if there are more infected individuals, more susceptible individuals, or people are in contact with others more frequently, the number of susceptible people will decrease more quickly. We momentarily skip the second equation to explain the third. The third states that the number of recovered individuals increases over time by the number of infected individuals who recover at a given time. Now, the second equation simply states that the number of infected individuals simultaneously increases by the number of people who just went from susceptible to infected, and it decreases by the number of infected people who have just recovered. So we see that the SIR model is a relatively intuitive explanation of how the number of susceptible, infected, and recovered individuals changes over time.
So as mentioned earlier, there is ongoing debate on whether or not ACE inhibitors and ARBs should be utilized in the treatment field. This is just to cover the scientific aspect of COVID-19 virulence. It is agreed that more data with the use of these drugs is desperately needed to guide more decisions regarding this choice, but recent evidence suggests ACE2 may actually be beneficial in those suffering from lung injury. Furthermore, the sudden withdrawal of RAS inhibitors in those already utilizing these drugs as treatment could be harmful down in the long run. For example, RAS inhibitors is thought to contribute to adverse outcomes of patients as well as hypertension, but there's insufficient data to support this claim. Back to that article I mentioned earlier, age and hypertension are key determinants in the outcome of disease advancement. We cannot give any guaranteed answers about their use clinically or physiologically since they have varied outcomes. For example, clinically, these blockers have no effect on the ACE2 enzyme. However, the same blockers can either have an effect or no effect physiologically, hence the need for more data. Finally, the last key point looks at the benefit of withholding withdrawal of RAS inhibitors in high-risk patients already using them. ACE2 degrades angiotensin II to angiotensin 1 through 7, reducing its effects on vasoconstriction, sodium retention, and fibrosis. It is essentially preventing harmful fibrosis in the body.
Finally, we can talk about the complications of modeling COVID-19 specifically. First, since COVID-19 is a global pandemic, it affects many different countries with many different backgrounds. Hence, we can't really use the same prediction methods or equations to predict the infection spreading in different populations. Another problem that stems from the fact that it's global is the variances in social distancing guidelines. Even in the United States, we can see that different states started these social distancing guidelines in different times and also adapted them in different ways. As you can see with this projection for COVID-19 deaths in Pittsburgh, the best case and worst case is very different depending on the social distancing guidelines that we put into place. Finally, like I brought up before with the SIR model, it seems like relapsing symptoms after showing brief improvement is something that's happening with COVID-19. This makes it much harder to really categorize where people are, and hence makes it harder to predict how this infection is actually spreading. As we saw, the scientific community has a very strong foundation for predicting infectious disease spread. Even so, modeling COVID-19 spread is a very hard task given these challenges. Still, we can't give up and we need to keep trying to predict to try to mitigate the spread of this virus. Here are the references. Thank you for listening.